Perfect, great. And it's a pleasure to be here. And first of all, thank you to all of you for joining such a wonderful conference. I just joined, and I can even imagine how much I just learned from the previous sessions. Perfect. Now let's focus on my session is mainly focused on regressions and classifications. So if you are new to machine learning, and guess what happened? This is the sessions for you. And after these presentations, I am overconfident you will get something about it. And then you will also know how to get started with your own machine learning project. By the way, my name is Jean-Joseph. I am a data and AI engineer and work for Microsoft as a technical trainer. I am also the founder and the co-organizer of Data Driven Community. Okay, under Data Driven Community, we have Cloud Data Driven, which is a user group we meet every Thursday at 12 p.m. New York time. We also have a yearly conference that called Feature Data Driven Summit. If you haven't registered, feel free to do so by just going to datadrivencommunity.com. Or you are free to connect with me. This is my, for some reason, let's see here. This is my QR code. You are free to scan it and connect with me on LinkedIn. Let me proceed with our next slide. First of all, I would like to say kudos to all of you who joined this wonderful conference, and special thanks to our organizers, sponsors. You know, without them, I don't think we would be able to learn from one another, right? And also what to expect. This is exactly what I'm pretty sure you are guessing in these fast-paced beginner sessions. Okay, also a great refresher for seasoned practitioners, right? We will focus on the core concepts and key differences between regression and classifications when it comes to machine learning. And also, due to limited time, we will skip the fluff and dive straight into how these models work, when to use one, okay, versus others, and also how to evaluate them. I guarantee that by the end of these sessions, as I mentioned, you will have the confidence and also clarity to kick off your own machine learning project. First of all, let's get started. What exactly is machine learning, Tim? I'm glad you asked that questions, right? Machine learning revolutionized AI by moving beyond rigid rule-based, right? Instead of relying on manually coded instructions, machine learning enables systems to learn from data, identifying patterns, making predictions, and also improve over time, right? This shift allows for more adaptive, scalable, and intelligent solutions across, I would say, different industries, right? Choosing the right type of machine learning can feel overwhelming, especially with so many algorithmic and approaches available. For beginners, it's often unclear, right, whether to start with regressions, classification, or something else entirely. Guess what happened? This session is designed to cut through that confusion by focusing on the core differences and use cases, right? So you will walk away knowing exactly how to match your problem to the right model. Did I say problem? Yes. Let's focus on the problem, right? As I mentioned, it's often unclear whether to start with supervised, unsupervised, semi-supervised, or even reinforcement learning. Why? Because each type serves a different purpose. So let's demystify how to start the right one, the right way, okay, for your project. The first thing is to identify your problem. I always state that, okay? Without problem, there's no value in AI because the intent of AI is to promote efficiency, productivity. So you have to first, okay, by engaging with business stakeholders to clearly define the problem within a business context. Let's put it this way. Why? Because a well-articulated problem, such as uncovering the reason behind customer churn, help align the team and establishes a clear focus directions. Once we identify the problem or task, our next step is to turn that problem or translate the problem into a specific, measurable questions that guide your data exploration. For example, instead of asking why are customers leaving, we can change that questions to make it more analytical, okay, and task oriented. We can change it this way. What are the top predictors of customer churn in the last 6 months, right? So consider now we have the problem. We turn the problem into analytical questions. So here's what next is the data. Is the data available? So understanding the data needed to answer your analytical question is a crucial steps in the project kickoff in the context of machine learning. This means identifying what type of data are required, whether the current data is sufficient or do we need additional data, right? Set to be acquired. All these questions have to be answered, right? So this still a structure of your data, whether if it's labeled, unlabeled, or partially labeled, or if there is absolutely no data, will directly influence the type of machine learning approach you should choose. Consider there is data. Yes, there is data. So if there is data, your first questions should be, okay, do I have a full data set? What I mean by a full data set thing, when the data have questions and answer, when the data have features and output, when the data have problem and solutions. So what I mean by anytime we have a full data set or labeled data, we are in the theory of supervised machine learning, right? So this mean we already know the outcome we are trying to predict, and we can train models to learn the relationship between input, features, and choosing non-output or outcomes, right? So supervised machine learning is powerful because it allows us to make accurate predictions, okay, in the context of classification or regressions, right, based on historical patterns. So the key is to determine whether your target variable is continuous in the context of regression or categorical in the context of classification. In other words, okay, in supervised machine learning, we deal with two types of problems. We either dealing with regressions or classifications, okay? And understanding the differences is key to choosing the right approach. Let's focus on regression problem. They are predicting continuous values from 0 to 1. This could be infinite. Think of questions like, for example, if you recall, I said we first need to start by identifying the problem. After we know the type of problem we are dealing, once we turn that into analytical questions and we have a full data set, that full data set can tell us if we have to go with supervised machine learning in the context of regression or classifications. If you ever have such problem where you have a full data set, where your question mainly related on numbers, like what will the temperature for tomorrow, how much revenue will we generate next quarters? So the output is the number that can vary across a range. And the interval is 0 and 1, right? So therefore, anytime we have to predict a value, that value is a number, and we have a full data set, we have to think of supervised machine learning, and the type of solutions we're looking for is regressions. Sometimes, team, the answer could be a class or could be a categorical data. So this is where classifications problems comes in. So such problem are predicting categories. So they come into two flavors, as you can see on the screen, right? The first one is binary classifications, where there are only two possible outcomes. So meaning an email can be fraud or not fraud, spam or not spam, okay? An email can be work or personal. So those are the labels. In the context of multi-class classifications, there are more than two categories, unlike binary, where we only dealing with two classes, right? So in the context of multi-class classification, consider if we have an email, we want to classify that email as personal, highly urgent, okay, spam, or work. So we have more than two classes. We cannot rely on binary. So we have to rely on multi-class classifications, right? But here's the thing, what happened after we analyze that data, we discover we only have problem or questions or features, but we don't have the solutions. So this is where, for example, we have partial data, where the data, not really partial, this is where we have what we call unlabeled data set, right? In the context of unlabeled data set, put it this way, if your data is not labeled, right, then you are stepping outside of the realm of supervised learning, right? And that's where other type of machine learning comes into the picture. Because if we don't know the outcome, consider if you have a tons of application log data coming into your data lake, or you probably log them as files, and you need to identify the root cause of why something is happening. Therefore, you don't have an answer. You cannot rely on supervised machine learning, because in a supervised machine learning, both must exist, the input and the output, right? So with that, we have to think of unsupervised machine learning. So therefore, understanding the type and structure of your data is critical. What do I mean by? If you have, for example, no label at all, you're likely looking at unsupervised learning. Unsupervised learning does not use label data at all, to be honest with you. It used for tasks like clustering, right? And dimension reductions or anomaly detections, where the goal is to uncover hidden pattern or grouping in the data without predefined labels. Think of it this way. But here's the thing. In a supervised, we have both problem and solutions. In unsupervised, we only have problems. The machine will tell us the solutions. There are cases, okay? There are cases, for example, where we may have other things, right? So what do I mean by? if we have partial of your data, right? I think when I'm looking at the slide, I, for those of you that are kind of new, let me remind you, in a in the context of unsupervised machine learning, this is just a recap, we have two types of problem. Those are the two main problems. We have what we call clustering and dimensionality reductions, right? In the context of clustering, it's about discovering natural grouping data point without any label. For example, grouping customers by purchasing behavior or segmenting users based on app usage, right? Algorithmic like k-means and DB scan are commonly used. In the context of dimension reductions, okay, they just help simplify complex data set by reducing the number of input features while preserving the most important information. This is especially useful for visualizations or speeding up model training. Technique like, as you can see on the screen, PCA, which stands for Principal Component Analysis, and also we have TSNE, are popular choices, right? So when your data has no labels and you are trying to explore structured or simplify it, unsupervised machine learning through clustering or dimensionality reductions is the way to go. But remember, unsupervised ML, there is absolutely there is data, but the data has no label or no answers or out no output, okay, on it. Now, consider team, if we have, for example, partial label, there are cases where the data happen, for example, in your data set, you may have a small amount of label data mixed with a large amount of unlabeled data. So with that said, you cannot think of unsupervised machine learning. Instead, it has to be semi-supervised. In a semi-supervised machine learning, right? So it helps us make the most of both. So therefore, it's combined supervised and unsupervised together, right? Semi-supervised learning, okay, leverage the small label set to guide learning while extracting structured or pattern from the larger unlabeled set to improve model performance. This approach is especially useful when labeling data is expensive or time consuming. In a semi-supervised machine learning, it helps solve classifications with limited labels. So what do I mean by limited labels? Think of it like when you don't have enough label example to train a reliable supervised machine learning. So with that said, you cannot only rely on supervised. So you have to combine supervised with unsupervised in order for you to be able to answer the questions uh, for those that doesn't have the answer, right? We also have what we call improving generalizations. So this leverage the structured in the unlabeled data. The model can learn better decision boundaries and also avoid overfitting. We have another one, what we call label propagations for spreading. So it used the few labeled example to infer labels for the unlabeled ones, right? It's effectively expanded your training set. This method bridges the gap between supervised and unsupervised learning, making it ideal for real-world scenario where label data is a little bit scarce, right? But here's the thing. What if there is no data at all to help answer your analytical questions? Then your problem likely involve learning through interactions where a system improves its decisions over time based on feedback. So this is where reinforcement machine learning comes in. Instead of learning from labeled examples, right? The model learn by taking action in an environment, receiving rewards or penalties, and adjusting its behavior to maximize long-term success, right? In a reinforcement machine learning, the core problem it solves is when a system needs to learn through trial and error to maximize long-term rewards. Think of it this way. This is ideal for situation where there is no historical label data to learn from, but the system can interact with an environment and receive feedback in the form of reward or penalties. Common examples include robotic, game playing, and recommendation system. So the goal is to find the best sequence of action that lead to the highest cumulative reward over time, right? So algorithmic like Q learning, deep Q learning, and SASA, okay, are commonly used to tackle these type of problem. So this is in a nutshell the type of machine learning. You can see the value of identifying your problem, right? So if I wasn't aware of the type of problem, how would I turn that into analytical questions? Moreover, how would I analyze that data? So it is ideal to start from here and make sure your analytical questions, when you turn your problem into that, meet your business expectations. So in summary, right? In summary, here's a in the context of choosing the right type of machine learning, right? Think of supervised machine learning like that. It is useful when you have a complete data set where all your questions have answered within that same data set. So what I mean by where your data mapped to features from features to non-label. Think of it this way. If you are working with unlabeled data set to discover pattern or clusters, right, or similar reactions, or you need to analyze the root cause of something, so therefore you don't have that answer. Because you don't have that answer, you cannot rely on supervised machine learning. You have to rely on unsupervised, right? Regarding semi-supervised, think of it where you have a huge data, but you have very, very few of your data that have answer or inside, right? And what you can do instead, you can combine supervised and unsupervised because you have a small amount of data mixed with a tons of data that doesn't have answers or label. So with that said, you have to take advantage of what we call semi-supervised machine learning. And if there is no data at all, you have to think of reinforcement, because reinforcement allows the machine to learn by interacting with an environment. Think of it like an agent that can analyze this state, okay, to choose what action and maximize reward. So in such machine learning, we normally start it most of the time with no data or no label data set is required. Okay. So therefore, our main goal is mainly focus on what we call supervised, because if you recall the session title, the art of regressions, right? So these sessions, anytime when I present it, it's always well received because of how I lay out the best way to choose machine learning. So now let's focus on regressions and classifications. As I mentioned, right, the focus is on supervised and semi-supervised. So I'm sorry, it's on supervised. So it's important, right, to point out that relationship between features and label are everything. So anytime when you're dealing with supervised machine learning, you should never minimize the relationship between your questions or features and answers or labels, right? The model's ability to learn and make accurate predictions depend entirely on how well the input feature explain the influence of the target output. So let's go and do a small simulations, and remember the goal is to focus on relationship to show you how relationship can impact your training process in the context of supervised machine learning. What I'm trying to emphasize is that for the model to learn effectively, there must be a strong and meaningful relationship between the input feature and the target output. Let me explain this to you. If I have, consider we have two grocery, okay, selling the same product, which is olive oil. One of them is selling it for $10, as you can see on the screen, and another one is selling that same product for $2. One is 10, one is 2. Okay? Where would we buy it? I'm pretty sure you are guessing we'll get it from Gear Food, because Gear Food is selling it for $2 and they are the same, they have the same quality, they're made by the same manufacturing, okay? And also they have the same ingredient. So with that said, I will go with the $2 to save money. Is that easy? What if I add one more color, which is location? In order for me to drive to JDJ food grocery, it will take me 5 minutes. And to drive to get food grocery, it will take me 1 hour. So now the decision change. What I'm trying to emphasize here to show you how relationship can change your own daily data statistic, which is a lot of time people minimize that. So now definitively we will take it from the one where we will drive just for 5 minutes. Okay, it's not worth it. But what if I add another column and say quantity? The first one, I will have to drive for 5 minutes. I understand. And I only need a quantity of 10. For the second one, I will drive for 1 hour and I need a quantity of 100. The underlying data statistic change. So with that said, we cannot, the predictions will change as well. So with that, it will be 100. So it's okay to drive for 1 hour, and by 100 of them, we can see the time to spend, it's worth it. So meaning when you're dealing with machine learning, okay, understanding supervised machine learning, right, those relationship, okay, they have strong they have to be strong and meaningful. That's the reason why you have to think of feature engineering to change the statistic of your underlying data set in order for you to give to make sure the data is ready to be trained, right? The model can generalize well to new data or unseen data set. But if the features are irrelevant or nosy, okay, the model struggles to learn anything useful. So that's right, understanding, selecting, and sometimes engineering the right feature is a critical step in any supervised machine learning. So let us go over this as I already show you. The simple example explain how strong, okay, this example we just went over, okay. So if the relationship doesn't fit the target variable in the context of supervised machine learning, we have to make sure we done some extra work to make that happen. Okay. So second, so what are the core differences? As you can see here, right, in the context of features, we have here, what is my mouse? I'm not sure. Here we have output. For the output in the context of classifications, we are dealing with a finite, what we call category, right? In the context of regressions, so we have a continuous value. So this can be infinite, as I explained. It could be from 0 to 1. What I mean by 0 to 1, it could be like 0 0.1, 0 0.50, 0 0.78, 0 0.99, and so on. This could be infinite. So with that said, if your problem is to check if an email, for example, happen to be a spam or not spam, so we're dealing with classes. So you have a finite category. So therefore, the data is not really in numbers. So with that, we have to think of classification. But if we want to predict the stock market price, we will definitely think of what we call regressions. All right. Perfect. So what are the goals here? Not sure why it is not showing. Just give me. So let's, for some reason I can't see it. I can't see my mouse. Is that what are the goals? In the context of goal for classifications, think of you are predicting class membership, and then whereas for regression, we're just predicting a quantity. What are the business use cases? As I explained, if you want to identify spam or not spam. Okay, so to summarize, because I do not want to go over everyone one by one, let me do a summarizations, right? Choosing between classification and regression, start with understanding the nature of your task or problem. If your goal is to predict a categorical or label, you're dealing with a classification problem. So this could be binary, spam or not spam, or this could also be multi-class, right? So meaning we are predicting for diseases. Such analytic predictions may have more than two classes, right? So on the other hand, if you are trying to predict a continuous numeric value, it's a regression problem, teams, like forecasting sales or estimating temperature, right? So the type of output you're aiming for determine the algorithmic evaluation matrix and modeling approach you will use. Keep that in mind. So always begin by asking, am I predicting a category or am I predicting in numbers? So that answer will guide your path. So consider you have already figured out what type of supervised machine learning you need. So your next step is, for example, think of development. So before we go over development, I would like to show you a simple code of linear regression. So consider when we think of linear regression, it's still regressions, because in machine learning, so logistic regression is classification, linear regression is regressions, okay? So in here, what I'm doing, I'm not sure what in here, what I'm doing, I'm importing linear regressions from learn that linear model. This is sklearn, right? What is this guide? This is MLflow. The goal of this guide team is to track, okay, the experiment process in the context of matrix and learn parameter. And it's also allow you, okay, to leverage hyperparameters as well, because consider during the training, we have two type of parameters. We have a learn parameters. Those learn parameters are the parameters where the weight that have knowledge about your weights and biases, right? And we have another parameter that called hyperparameter. Hyperparameter is a type of parameter that doesn't learn during the training process. However, they give you access to control the experiment process, like batch size, regularization, weight, number of epochs, and so on. There's so many things we can think. Let's keep it level 100 as this is the beginner level. So in order for me to track any kind of matrix, I am importing MLflow, right? So now this is where I'm starting my MLflow, and then this is where I am setting up the model instance. You can clearly see this guy is the one that was here, right? Yeah, I'm not sure why my mouse is giving me a hard time. Perfect. So now this is where my training stopped. So in the context of training process, remember the goal is to focus on regression and classifications, but in the context of training process, we have to split it, right? The splitting must be done before the feature selections in order to prevent data leak. So now what I'm doing, consider I already done the splitting and I already done the feature selections, right? So now in the context of training, we can have 2 or 3 sets. We can have, when we have 2, we have a training set and a test set, because it is not ideal to train the model to leverage your entire data set. We'll go over that very, very soon, okay? So it is ideal to split it. There's different rules. If you know your data, you can go between 85 to 15. Sometimes 80, 20, sometimes 75, 20, where the model, you allow the model to see 75% of the data and 25% you leave that for test. Sometimes we may have 3, which is a validation test. This is most likely in the context of advanced modeling and optimizations. So we can bring a third set, and we call that what we call validation. So this is where I'm logging. Anytime when you have to explicitly focus on a specific matrix, or for example, parameter, all those custom values can be added. So in here, this is a parameter, and this could be matrix as well, a custom matrix. But if you only care about the matrix, there's no special parameter you want to track, the AutoML right here is good enough, because once you turn on MLflow that autolog, MLflow that autolog, that's good enough for you to track that, because the role of MLflow by default is to track your end-to-end machine learning experimentations, okay? So now consider if we have to do a classifications. In a classifications, instead of we importing a linear model, all we have to do, we are importing a logistic. Anytime when you hearing logistic regression, think of classifications. So therefore, you will be dealing with a categorical data set. So this is the same, for example, line of code. You don't want me to repeat myself, but yeah, instead of creating an instance of linear regressions as the focus was for classifications. So with that, uh, this is the instance. Instead, I'm using logistic, and those are the same code. Your question would be, for example, what platform that can help you with the development? If you ask that, this is where Azure Machine Learning comes in. It supports the full level um, ML or machine learning lifecycle, okay? And from, I would say, explorations, from ingestions, explorations, and also building and training. Moreover, evaluating, deploying, and monitoring your entire end-to-end machine learning pipeline. Azure Machine Learning can help you. You know what I like? Whether you are working on promises, right, or across multi-cloud like Azure, AWS, or Google Cloud, Azure Machine Learning Workspace offer flexibility through Kubernetes and Azure Arc integrations. It's also support what we call CI/CD, okay, making it ideal for production-ready enterprise scale machine learning workflow. So now consider you leverage Azure as your platform to proceed with your machine learning pipeline. So your questions, okay, could be, what are the key concepts from raw data to prediction model? So here's the thing. If you ask that question, I'm happy you did. The first thing you have to think of is the pre-processing. This is the foundation step where what data is cleaned and transformed into a usable format. It involves handling missing value, encoding categorical variables, right? Normalizing numerical features, and splitting the data into training and test set. Effective pre-processing ensure the model receive consistent and meaningful input, which is crucial for accurate learning. So once we ingest that data, okay, the next step is think of training, right? During the training phase, the model or the machine learning algorithm learn pattern from the pre-processing data. So the model adjusts its internal parameters to minimize the error between its predictions and the actual outcome. So this phase often involves selecting the right algorithm. Like we can think of decision tree, neural network. Even we can bring like tuning hyperparameters and adhering to improve performance. Consider we process that data, we make sure that data is clean. Okay, we perform nice model data splitting and feature selections, and we start with the training. After the training, the next phase is for evaluations, right? So the model has to be evaluated using either, we can even bring a separate data set if we want to. If you want to go advanced, I'll keep it a little bit beginner level, okay? So to test, to perform advanced optimization. So we can bring a validation data set, right? Perfect. We also have to think of metrics such as accuracy. If we want to maximize for accuracy, it could also be precision, we call F1 score, or if we have to minimize error, we can even think of what we call mean square error. Okay, they are used depending on the task. Like if you're dealing with classification, your intent is, technically speaking, maximize your accuracy, but you need to understand the underlying data set matter. Sometimes you should never only rely on accuracy, even though if you're dealing with classification, right? So we might need to, think of precisions, or recall, or even F1, just to make sure the model is ready for productions, right? But in the context of regressions, the goal here is to minimize error, right? So you can see the evaluation steps help assess how well the model generalizes to unseen data and whether it's ready for deployment. So consider now you are done with the evaluation and that meet your expectations. Your next step is for deployment. In the context of deployment, right? So you have to think of so many things before you deploy your model after the evaluations into a production environment, right? So where think of it is you create a bridge, right, where it can make real time or batch predictions, right? So deployment include integrating the model into an applications or services, monitoring its performance, and updating it as needed to maintain accuracy over time due to the changing data pattern or concept drift. There's so many things we can think. After the deployment, that doesn't mean we end, right? So understanding the first steps you are seeing on the screen now uh, can be repeated multiple times even after the deployment occur. Okay, so thank you so much. I hope you get something after this presentation. If you have a question, feel free to ask, and it was a pleasure to have all of you, and thank you for the invitation.